Okay, good morning or good afternoon, depending where you are. I'm in China, so I call it good morning. But we will start our series of lectures in this month and on the literature and history of mathematical science, and it's hosted by CMSA in Harvard, together with YMSC in Tsinghua University. And we are glad that we have been extremely successful in this series with a lot of great speakers. And today we have another great speaker from UCLA. And to give the detail, Sergey is going to host, to chair this talk. So let's start, Sergey.
Hello, everyone. We are very lucky to have Amit Sahai giving today's Mathematical Sciences Literature Lecture. Please allow me to introduce our speaker. Amit Sahai is a professor of computer science at UCLA and the director of the Center for Encrypted Functionalities there. I have to mention that he also serves as an advisor to the Prison Mathematics Project. Among many of his awards and recognitions, Professor Sahai was invited to give Distinguished Cryptographer Lecture Series at NTT Labs. He was named Alfred Sloan Foundation Research Fellow, as well as a Fellow of the ACM. His research interests span theoretical computer science, foundations of cryptography, and computer security. Professor Sahai is famous for his contributions to functional encryption, zero-knowledge proofs, secure multi-party computation, and of course, indistinguishability obfuscation of today's talk. Everyone is very welcome to ask questions. Please post them to the Q&A tab, and I will read them in the end, unless you are concerned with some clarification, and then I will interrupt the speaker. Professor Sahai, the floor is yours.
All right, thank you so much for that really kind introduction. And let me just say that I would really love to take questions throughout the talk. Don't have to be clarification questions, anything goes. I would love for this to be as interactive as it can be. Let me go ahead and share my screen. Give me a moment. All right. And I hope that is visible to everyone. So yeah, as Sergey mentioned, I'm going to be talking about indistinguishability obfuscation, which concerns the question of how to hide secrets within software. So before I give you anything very technical about this, I'd like to take a step back and just think about what this means sort of philosophically, okay? So suppose for a moment that you want to keep a secret, right? But unfortunately for you, there's an adversary that has actually captured your entire brain. So he's opened up your head, stuck out your brain, and is holding your brain in its hands. And not only that, but it can read and tamper with the activity of every single neuron in your brain while you are thinking about some secret that you want to keep hidden. Okay, and when I mean that he can read and tamper with the activity of every neuron, I mean that as completely as possible. So he knows the location of every electrical charge that's going through your brain. Everything about your brain is known to the adversary. Okay, and somehow you are tasked with the challenge of keeping a secret from an adversary that can literally read your mind. Right, it can see everything that's happening inside of you. Okay, so obviously, I hope this never happens to you. It's never happened to me. So far as I know, it's never happened to anyone that we know. That would be quite bad. But if you think about it, the computer science analog of this situation is actually extremely common, and that's what we'll be talking about today, right? So it's actually very common that an adversary gains complete access to some program that has been developed by someone, right? And the program is perhaps supposed to be kept secret, but the adversary captures it. And what we're asking today is it possible to somehow transform a program so that it can keep a secret even when it has been completely captured by the adversary. That is what we call obfuscation. That's going to be the subject of today's talk. And what do I mean? I really mean everything is known to the adversary. So to be clear, there's no trusted hardware. There's no portion of the computer that is, kept hidden from the adversary. The adversary can see everything that's going on in that computer. There's no interaction. It's not talking to some external server that will be able to keep some secret for you. None of that is possible. And it's just an ordinary program. It has ordinary inputs and ordinary outputs. They're not encrypted inputs and encrypted outputs, just completely normal inputs and outputs, okay? And once again, it's running on a single, completely ordinary and public computer, okay? So that is what we're trying to think about today, right? And just taking a step back, I was asked to sort of also give sort of a personal view of this as well. I hope that all of you listening today will listen to this and think, wow, that sounds crazy. That sounds impossible, right? And in fact, sort of my view of mathematical cryptography as the field exists today is that really doing seemingly impossible things is what we do. That is what it is to be a cryptographer. And in fact, this is really what drew me to cryptography in the first place. Long, long ago, I thought I would want to work in algebraic topology, but then I heard some things about cryptography and in particular these impossible things, and I just was hooked. I couldn't think of doing anything else. And of course, obfuscation is just one such example. And let me just sort of mention a few other examples. In fact, the impossible thing that actually drew me to cryptography was the notion of a zero-knowledge proof that was invented by actually one of my PhD advisor, Shafi Goldwasser, together with Mikhaili and Rakov back in 1985. And the zero-knowledge proof is this fascinating object which allows a prover and a verifier to have a conversation back and forth with each other. And at the end of the conversation, the verifier is completely convinced that the statement being proven is true, but he has provably no idea why the statement is true, or at least no additional idea. If he already had some suspicion, he can maintain that suspicion at the end of the conversation. But the conversation should not help him in any way understand anything more about why that statement is true. And again, seemingly impossible, but in fact, doable with beautiful mathematical ideas. Another example is the notion of a succinct proof introduced by Killian back in 1992. And this is a situation where the prover sends a short message to the verifier that is completely convincing, and yet it could be that the proof is actually shorter than the theorem statement. So it takes longer to read the statement of the theorem than to read the proof. Okay, now, of course, verifying that proof will take longer. I'm not promising you anything about that. But the proof itself can be incredibly tiny and yet nevertheless be convincing to a verifier. Again, seemingly impossible, but something that we do in cryptography. In fact, something that we may have been sort of inured to just by time is the notion of public key agreement. So, you do this every time you buy something from Amazon, right? So what is this? Here we have strangers, Alice and Bob, that have never met each other before. They've never had any prior communication. And they undergo a public discussion that's in the, everyone can see it, see what's happening. In particular, our eavesdropper Eve can see exactly what Alice and Bob say to each other. And yet, after this public discussion, Alice and Bob share a secret key that is unknown to Eve, completely unknown to Eve. So, once again, this is something that, if you think about it for the first time, it sounds crazy, even though we do it every day online. It sounds crazy, and indeed, for the many thousands of years prior to 1976, if you would ask someone, "Is this possible?" It sounds completely nonsensical, right? Everything is in the public. How can they? Everything is public here. How can possibly Alice and Bob have a shared secret? And yet, this is something that we do every day, all of us now. And this can be extended to multi-party group key agreement. We could have Alice, Bob, and Charlie, and again, they just all talk publicly and somehow share a group key. This is just yet another example of something that just seems fantastical and yet this is sort of bread and butter, ordinary, everyday life for us mathematical cryptographers. So, so this is what we'll be. These are the examples of these kind of impossible things. And in fact, one reason to get you potentially excited about obfuscation is that, in fact, obfuscation implies all of these things. So all of these four that I just given you are just small examples of seemingly impossible notions that are implied if we can achieve obfuscation. So that's sort of one reason for us to think about it. Now, before I continue, I would be remiss if I don't mention something that's really very, very important, which is about conjectures and cryptography as a mathematical discipline. So, I say we can do these seemingly impossible things, but really all I can say is we think we can do these seemingly impossible things. Why is that? It's because almost all of cryptography, in particular all of these amazing things that I'm telling you about, they are based on unproven complexity conjectures. So we're making certain conjectures, and if those conjectures are true, only then can we do all of these things. And that's a little bit of a downer, but there's some good reason for this. One of the things is that all of these complexity conjectures that we're making are at least as hard to prove as settling the P versus NP question in the negative, showing that P is not equal to NP. That's one of the hardest ways to earn $1 million, as I'm sure all of you know. So these are, in fact, very significant conjectures in the sense that we are nowhere near, we have no idea how to prove these conjectures at all. If I had a good idea for how to approach the P not equal to NP question, that's what I would be doing. I wouldn't be here talking to you. I would be spending all my time trying to prove that P is not equal to NP. But sadly, as of 2021, as far as I know, we don't even have any good approaches. We don't even have any good ideas about how to attack this conjecture and wrestle with it and prove it. And in fact, it goes the other way as well. So almost all of these interesting cryptographic capabilities that we're after, not only do we currently need these conjectures, but in fact, they imply that P is not equal to NP typically. Most of these things imply that P is not equal to NP, for example, key agreement. And therefore, we really are stuck. We just have, if we really wanted to show how to achieve all of these amazing cryptographic capabilities, then we would first have to settle that the P versus NP question, again, by showing that P is not equal to NP, at the very least. And in fact, these conjectures are typically significantly more challenging than showing that P is not equal to NP in some qualitative sense. So then what do we do? Either we just give up, either we just say, all right, well, no point doing any crypto. Let's first try to work on P not equal to NP. But unfortunately, that hasn't really worked out so far. So instead, what we have decided to do as a community is to try to build up all of these fascinating and seemingly impossible cryptographic objectives based on conjectures, but only using long-standing conjectures. Only conjectures that have really been around for a long time. Ideally, these are so-called win-win conjectures, where if someone really was able to refute the conjecture that we're making, then it would have some rather remarkable consequences in some other area of mathematics or computer science. So that's kind of what we have settled into as a field in cryptography. We have to make conjectures, so we want to rely only on sort of long-standing conjectures. And within our field, we call these well-studied assumptions. Assumptions because we're assuming the conjecture to be true, and well-studied, hopefully, because they've been around for a long time and looked at by many eyeballs and many hours of sleepless nights and also dreams and other such time. So, right. So it turns out that, in fact, specifically when we're talking about obfuscation, actually a crucial thing that'll come up that we'll see later on the talk is actually about the role of conjectures in mathematics. And of course, we all know that conjectures are important stepping stones towards sort of results that we care about. And perhaps this is more obvious to non-cryptographers, but what we'll see today is that making stepping stone conjectures are also very important towards results that will also finally be based on a conjecture. So even if we want to make eventually build something based on a well-studied conjecture, then it's useful to make conjectures along the way. But I'm getting a little ahead of myself, so let me sort of turn back to the history of obfuscation, talk to you a little bit more about this problem, and then I'll come back to this and hopefully you'll see what I was talking about. All right, so obfuscation, again, beautiful, fantastic notion. It's actually kind of been in the air for a very long time, and it's hard to pick sort of an exact point when it was first introduced, but at least it dates back to 1976 and the classic Turing Award-winning work of Diffie and Hellman, which introduced public key cryptography. Many of you may know that Diffie and Hellman, they gave a excuse me, a protocol for key exchange. But in fact, they only defined public key encryption, but did not know how to construct it. And one of the major open problems in that work was to actually construct a public key encryption scheme, which was then resolved for the first time, or the first conjectural way of doing that was by RSA. But in fact, back then, when they didn't know how to build public key encryption, Diffie and Hellman conjectured the possibility of what they called a one-way compiler that would somehow take a program and compile it into a new computer program in a way that somehow hid what the original code was. Back then, they didn't have any formal definitions. They didn't explore it very rigorously, but they still talked about it specifically in the context of cryptography and the power that they could imagine it having. So, of course, since then, as a field, we have looked at many, many interesting notions in cryptography. I mentioned a few of them just now. But when it comes to sort of hiding computations, again, we have a very long history in cryptography and sort of conjecture-based mathematical cryptography. And sort of one of the very closely related concepts, which is introduced by Turing Award winners and Abel Prize winners, backed by Andy Yao, Goldreich, Micali, and Wigderson, Benno Goldwasser and Wigderson. What they showed was that, again, under long-standing conjectures, if certain conjectures, complexity conjectures, are true, then sort of viewed from the lens of obfuscation, viewed through the lens of our brain analogy, what they showed was that if you take the sort of brain that's doing the computation, but you subdivide it into these little compartments, and now we say that the adversary can see what's going on, let's say, in one of those compartments, or in the most advanced form of this sort of secure multi-party computation, let's say in all but one of these compartments, right? And what they showed, again, very surprising, seemingly impossible, remarkable results, is that even if an adversary can actually see what's going on in the brain, in the sort of collective brain of these different participants who are talking together to perform some computation, even then we can maintain secrecy. And sort of at a very high level the idea was, let's take whatever secrets are present and sort of spread them out using an idea called secret sharing in such a way that the only way the adversary can obtain the secret is if he sees all the parts of the secret. And in this notion of secure multi-party computation that was introduced in the 80s, there was always the assumption that at least one of the parties, at least one of these little segments of the brain, is actually completely blocked to the adversary. Okay, and you can see that was absolutely crucial to also the solution idea that was introduced in those works. That it's very important that the adversary can't see everything that's happening. There's at least some part that he's blocked from seeing, and that is exploited to achieve this otherwise remarkable and impossible seeming idea of protecting a computation, even when an adversary can see almost all of it. So again, these were ideas back in the 80s, beautiful, extremely influential remarkable papers that dealt with this is still an active area of research today. But the main thing I wanted to emphasize here is just how fundamentally different it is from what we're trying to do. So in obfuscation, remember, nothing is hidden. The adversary can see the entire brain. There is no part of it that is actually kept secret from the adversary. Whereas in secure multi-party computation and other concepts that we looked at in cryptography over the last several decades, it was always required that some portion of this computation is completely hidden from the adversary. And again, in our situation, no part of the computation is hidden. And that's what makes this problem such a different problem, and why it's sort of really been such a major challenge over all these decades. Something that we really didn't know how to attack for a very long time. So, all right, let's try to get a little more precise in terms of exactly what we mean by obfuscation. So, if you think about it for a moment, we'll see that not every program actually even has any secrets within it. So what do I mean by that? Let me give you an example, right? Suppose I have a program that takes some input X, and it has some constant built into it. You might think of it as potentially a secret, some S. But what the program does is simply compare X versus S, and if X is less than X, it outputs 1, otherwise it outputs 0, right? Now, it takes just a moment to realize that no matter what I do to this program, no matter how I might try to mungle it up or modify it, as long as I maintain its functionality, there's no way in which there's any secret here, right? Because an adversary can simply perform binary search. It can just look at the range of values that X can be, and just figure out what S is based on a few queries to the program, right? So as long as my obfuscation procedure is preserving the input-output behavior of the program, there is no secret present here, right? And more generally, we can see that for obfuscation to make sense, for any kind of secrecy to be plausible, the program must at least be unlearnable based on just input-output access to the program. So the input-output behavior of the program must still preserve certain secrets for it to even make sense, for the problem to even make sense, right? And this observation also gives rise to sort of a very natural hope, like a definitional framework for us to explore, which is the idea of a virtual black box, right? So the idea is, can we somehow obfuscate some program P so that it's only as useful to the adversary as a black box that you're only allowed to query with inputs and see what the outputs are, right? That was sort of a very natural hope. And in fact, back in 2001, in a joint work with a couple of your colleagues there at Harvard, Barak and Vadhan, along with several other co-authors, we sort of took a systematic study of this idea of a virtual black box notion of obfuscation. And unfortunately, we ruled it out. So let me tell you more about what I mean by that. And by the way, again, please do stop and ask questions at any moment. I would really love to address them. But let me continue. So in what sense did we rule it out? What do we mean by the virtual black box is not always possible? What we showed is the following, a little more precisely what we showed is the following, that there are certain very contrived programs that I call self-eating programs, for which black box obfuscation suffers from explicit attacks, okay? And I don't have time to sort of explain to you exactly how that works, but let me give you the very high level idea. The idea is that we're somehow going to create a program that'll have some secret built into it as a constant, right? But what the program does is somehow, it doesn't exactly do this, but it checks if the input is itself a program that is equivalent to itself, right? So it checks if the input is somehow a program that's equivalent to P, this program P that we're constructing, okay? If you want to know more, it's really, we more feed the program to it 1 byte at a time. Sort of we split it up into chunks and feed it into 1 byte at a time. But in any case, this is the overall idea. Somehow the program checks to see if it's being fed itself or fed something equivalent to itself. And then if it sees that the input was actually equivalent to itself, it just throws up and outputs its secret S. Otherwise, it outputs 0. Okay. So why is this a counterexample? Well, if I only give you black box access to this program, if all you can do is provide inputs and see what the output is, right? If this secret was chosen at random, let's say from some large exponential space, then the probability that you would be able to guess a program equivalent to X, given only input-output, given only input-output access, is negligibly small, right? It's exponentially small. And so to a efficient adversary, to a sort of an ordinary polynomial time, Turing machine adversary, if it has only black box access to this program, with overwhelming probability, that black box will just look like an always 0 black box, because no matter what program I give it as input, it just outputs 0, because my probability of having guessed a program equivalent to P is exponentially small, right? So clearly, for such a efficient adversary, getting black box access to this program is completely worthless and gives no information. However, if you give me any obfuscation of P, it's at least equivalent to P, so I can feed it to itself and it'll just throw up its secret S, right? So in this way, we see an explicit attack. We see an explicit, very contrived program that we know it just can't be virtual black box obfuscated, right? So maybe we'll take just a moment to take a step back and think about this sort of philosophically. So I should note that all the known negative results for obfuscation only apply to such pathological scenarios. Sometimes we can be more clever about exactly where we insert the pathology, but it's still always some kind of pathological situation like this. So this definition of virtual black box is actually not necessarily a bad definition with regard to any specific program you may want to obfuscate. However, this negative result still presents a major roadblock to being able to prove anything, right? Because we know for sure we will never be able to prove a theorem that says, assuming certain longstanding conjectures, it is possible to virtual black box obfuscate every program. That's just false, right? Because we have an explicit counterexample. Because of that, we kind of had no choice but to think about alternative definitions. And in fact, in that same paper, in the 2001 paper, we also proposed another definition, which can be seen as a kind of variant of the virtual black box definition. And here's what it says. And just warning, the only part of this talk that will have something that is completely formally described will be this slide. After that, I'll ask you to bear with me. But let me sort of get you started on this definition a little bit, piece by piece. And again, this is a place where I would absolutely love to get questions. So our obfuscation algorithm is itself a probabilistic polynomial time algorithm. It can run in time polynomial in the length of the program that it's being given as input. It can toss coins whenever it wants, okay? The result of the obfuscation should be another program that is equivalent to the original program. And the new program that is created by the obfuscation should only be polynomially slower than the original program, okay? And now, I need to tell you what exactly do I mean by a program, right? What is a computer program? So it'll be very convenient, and it's without loss of generality. Excuse me. For
Amit, we have a question.
Absolutely. Thank you.
By allowing only programs that are unlearnable using queries, how much of the total space of programs will forego?
Good question. Good. So, right. First of all, I don't know of any good measure on the space of programs, so I don't know how to answer that with a number. I can't say it's, we lost 23% of programs. But let me just say that there is no shortage of programs that are hard to learn, right? Coming from a cryptographic point of view, right? You could imagine a program that, let's say, digitally signs messages that begin with the name Amit Sahai, right? So this is a program that'll have built into it a cryptographic signing key, right? But the outputs of that program would only be signatures on messages. And if I only had black box access to such a signing oracle, then the signing key should remain hidden, right? So in cryptography, certainly we encounter unlearnable programs all the time. Now, outside of cryptography, it's a little trickier, definitely, but you know, we would imagine that we would imagine that there should be many circumstances in life where you can't figure out exactly what the program is doing just by observing its inputs and outputs. I hope that helped as an answer. All right. Well, let me continue with this definition of indistinguishability obfuscation. So as I said, I'm going to need a way of representing an arbitrary computer program. And the way that we'll think about it is as representing P as a Boolean circuit, right? So a Boolean circuit is extremely convenient for us because, first of all, the running time of a Boolean circuit is always the same, no matter what the input is. You just have to evaluate every gate in the circuit. So there's no dependency on input in terms of running time, which is very nice. The way to measure running time is simply the size of the Boolean circuit, the number of gates in the circuit. And it's been known, you know, since the 70s that every computer program can be converted into an equivalent Boolean circuit once you fix the input size. So, so this is without loss of generality, and it's just very convenient for us to think about things that way. Okay, so that is the polynomial slowdown property. And then finally, we have the main, you know, property, which is the security property. And what this says is if we have any two equivalent programs, P0 and P1, of the same size, okay? And by equivalent, I mean they have identical input-output behavior. So really, P0 and P1 are just two different implementations of the same underlying function, okay? If we have such pair of equivalent programs, P0 and P1 of the same size, then no polynomial time adversary should be able to distinguish between the obfuscation of P0 or the obfuscation of P1, okay? So this is the definition that I'd like to unroll a little bit for you. So here's sort of a completely quantified version of this definition. I'm just going to guide you through it, and hopefully, if you get this definition, then the rest of the talk you'll be able to sort of morph this definition to the appropriate notion. It's also okay if you don't want to understand this definition. Just bear with me for a couple of minutes, and then we'll move on. So what is this definition saying? We're often talking about no polynomial time adversary, right? So what we do is we simply have a for all quantifier over all constants, alpha, beta, and gamma, greater than 0. This is going to be the exponent in the sort of polynomials. And we say that for any such triple of constants, for large enough values of n, if we have size n to the alpha adversaries and size n to the beta programs P0, P1 that are equivalent, that is for all x in 0, 1 to the n, P0 of x equals P1 of x, and these programs are required to only have n inputs, okay? So if we have these equivalent programs, then we want to write down this idea that no polynomial time adversary can distinguish between these two things, and we write it down in this way. We look at the probability that the adversary outputs 1 when given the obfuscation of P0 versus the probability that the adversary outputs 1 when given the obfuscation of P1, okay? And we say these two probabilities are closer together than any inverse polynomial. So eventually these probabilities get closer to each other to within any 1 over n to the gamma, right? And this, again, remember, was for all gamma greater than 0. So this just formally captures this idea that the obfuscation of P0 is indistinguishable from the obfuscation of P1 to any efficient adversary, okay? And again, I would love to take a question about this if there are any. And hosts are also certainly allowed to ask questions as well. But this is the idea. This is how we formalize it. And in general, I'll be using this kind of idea many times in this talk. So the way that we write it down is I'll write IO of P0 is computationally indistinguishable from IO of P1. And this notation encodes this definition. It says that for every adversary, the probability the adversary outputs 1 on IO of P0 versus the probability the adversary outputs 1 on IO of P1 are within any inverse polynomial factor from each other, okay? And again, we call this computational indistinguishability and denote it in this way, okay? So this is our notion of indistinguishability obfuscation. It is definitely not as intuitive a notion as virtual black box obfuscation, but still it does have some interesting intuition behind it, right? It says that basically if I have 2 different implementations of the same function, then which implementation I started from is hidden by the IO obfuscator, right? And another way of thinking about that is that what it is a kind of pseudo canonicalizer, right? So if there was a way to create a canonical program for a given function, right, then that canonical program would be the same for P0 or for P1 because they compute the same function, right? So if IO of P was somehow outputting a canonical form of the program, that would satisfy the definition of indistinguishability obfuscation, right? Now, of course, we're not actually doing that. We're not actually computing a canonical form. Instead, we're only outputting something that's sort of indistinguishable from a canonical form. And therefore, we know that whatever IO of P reveals, it can't be revealing more than some canonical form of the underlying program, okay? And that's somehow the way in which we can make use of this definition, okay? And I'll just briefly mention that it's a very curious fact. I mentioned that most things in cryptography imply that P is not equal to NP. That's actually not the case for IO. So if P equals NP, then what happens is the polynomial hierarchy collapses. And in that case, computing canonical forms actually becomes efficient. It becomes possible to do in efficient polynomial time. So then IO actually exists. So IO occupies kind of a funny position in cryptography in the sense that it doesn't actually imply that P is not equal to NP. And that means that I was in fact lying to you earlier when I said that obfuscation implies all those other impossible, seemingly impossible things. What I actually meant was IO plus one of our sort of minimal complexity conjectures, usually the conjecture that so-called one-way functions exist. Those 2 things together imply all these other wonderful things that we have in cryptography. But let me just cop to that lie and sort of move on. I think this is something that makes IO kind of different and again, just sort of very curious in sort of the place that it occupies in cryptography. All right, so great. So now I have a definition, right? It's not impossible. Sorry, I should have mentioned that if you take a look at this definition, right, why doesn't the counterexample that I mentioned earlier, why doesn't that apply to this? It's because suppose that P0 was one of these self-eating programs, right? Well, then so is P1, right? In that case, both IO of P0 and IO of P1 would allow an adversary to recover the secret. And since it's actually allowed in both sides, it's no contradiction, right? It doesn't contradict the definition of security because in this definition, it's okay. You know, we are actually allowing you to potentially learn a little more than you could learn from just virtual black box access, okay? So, and indeed, one natural question that might arise is that this seems like a weaker definition, or certainly doesn't seem like as, you know, intuitive a definition as virtual black box. Is it still useful? turns out it's extremely useful. And we have a name in our field called obfustopia, which is sort of all of these interesting things that one can do if we assume that I/O exists, together with other sort of very conservative long-standing conjectures. And here I just given you a few examples. I won't bother to define them. I already mentioned two of them, group key agreement and these highly succinct proofs. Again, I wish I had time to tell you more about this, but there's a technique that we invented in the joint work with my former student, Brent Waters, that we published back in 2014, called punctured programming, where we sort of show how to take a program and sort of puncture it and sort of massage it step by step so that it alternates between steps where we maintain the functionality and therefore can apply I/O, and steps where we make some very tiny change to the program and we can apply some other conjecture, like one-way functions existing. And we can use that as sort of a technique. It's also called I/O gymnastics in our community, to sort of leverage the power of I/O and really achieve a remarkable number of objectives. Just in the first couple of years after we published our work, there were well over 100 papers that were published showing just a remarkable variety of different applications that I/O would have in cryptography, including many that to this day, the only way we know how to achieve them is via I/O, right? So definitely a very well-motivated question from a theoretical mathematical cryptography point of view, okay? So, all right, let's now jump into the question of how do we actually get this thing? How do we get I/O? So I'm just going to give you a very brief summary, biased towards things that I like and things that help me talk about what I'm going to talk about today. But very roughly speaking, sort of the first era was the first decade or so after we introduced the definition of I/O. And really, it's just, you can hear crickets sort of chirping in the background. They're just sort of a graveyard of lots of unpublished ideas that didn't work. There were a few impossibility results as I'm building upon the one that I mentioned already. But really, there was hardly any progress for a decade. In fact, no published work in mathematical cryptography based on any kind of conjectures for constructing I/O. Now, you might wonder, what about all those hackers, right? Maybe this is one of those cases where we theoreticians are behind the game, and out there, clever hackers have come up with all kinds of clever ways of obfuscating. Turns out the reality is the exact opposite. There are, in fact, contests that are held by, really the absolute top people in this field. And this is just an example from 2017, the white box cryptography contest for obfuscating something called the AES function with a fixed key. And as you can see, 94 different teams submitted various obfuscations, and all of them were broken. And in fact, there were almost 10 times as many breaks, as many ways of defeating the obfuscation methods than there were actual obfuscation methods that were proposed. So, hackers have no idea how to do this either, is the bottom line. It's not like we're behind. It's quite the opposite. It's an extremely important problem in practice, and so people do try various tricks and things, but they just present a sort of a small speed bump in practice, and basically everything gets broken. Okay, so practice hackers, they're not helping us either. Okay, so then things sort of changed back in 2013. This was in a joint work with a couple of my former students, Sanjam Garg and Brent Waters, together with some colleagues that used to be at IBM Research at that time, Craig Gentry, Shai Halevi, and Mariana Rekova. And there we looked at some new conjectures, or I shouldn't even say that. We just sort of proposed a mathematical construction for I/O based on a notion that we call cryptographic multilinear maps that I don't have time to go into. I may just mention a little bit about it later, but anyway, there were some proposals that had just come out, and we had an idea of how to maybe use that for I/O. And our conjecture was basically that our scheme was secure. We didn't we didn't have any argument. We just said, hey, looks interesting. Maybe it's secure. So it's a very complicated conjecture. New, maybe okay. That was sort of our hope. And in fact, it was refuted. So those conjectures were refuted, and in fact, the specific candidates were broken. This was well, one of the works here was a joint work with Miles and Zandri, where we introduced something we called annihilation attacks that pretty catastrophically break the approach that we had earlier proposed in 2013, and kind of refuted the underlying conjectures, and also destroyed the security of the resulting I/O schemes. So that was kind of some bad news. There was also some work trying to at least massage the assumptions, still using cryptographic multilinear maps, but at least making the conjecture cleaner, something that could actually, one could look at and understand what the conjecture is. Unfortunately, those conjectures were proven false. They were refuted by a sequence of works, starting with the beautiful work of Chion et al. So that was sort of the unfortunate situation. There was a little bit of a side. So in some joint work with several of my students back in 2016, we proposed a weak model of cryptographic multilinear maps. And again, a fairly complex conjecture under which we could build I/O. I do want to say that as of today, there's still no attacks known on that particular construction, those constructions that we had. However, they're still very far from a well-studied assumption or some long-standing conjecture. They're pretty complicated, and it could be that just not enough people have bothered to read our papers, and that's why there are no attacks. But it is true that there are no attacks on them. But again, still very far from kind of the guiding principles that we have in mathematical cryptography, the kinds of principles that people like Avi Wigderson and his buddies sort of laid out for us, which was to try to sort of push things down to well-studied assumptions. So there was another line of work, that long line, quite a deep line, that I'll talk briefly about a little bit later on, that showed how to take a few well-studied assumptions that unfortunately also I won't have time to talk to you about, but I'm happy to answer questions about them. One related to low-depth pseudorandom generators, and another called the learning with errors assumption, together with a new conjecture about degree 3 cryptographic multilinear maps. Again, sorry, I don't have time to define them. But unfortunately, it turns out that the degree 3 version of these objects were just as broken as the general version of these objects, and the same sequence of attacks that we had earlier actually applied. So once again, we had now quite nice looking conjectures, but that were false. And in fact, this is an area which, I'm sorry, I'm not defining it, but precisely, but this is an area where a lot of mathematicians have also helped us to try to think about how we might be able to do this. We've had a couple of workshops. One was at AIM in San Jose, another one was at Banff, where many different mathematicians from different areas came together to try to think about how we might be able to construct these objects. There was a proposal by Ming Day based on Ital cohomology, but unfortunately those two were either broken or just insufficiently implementable. Like they weren't efficient, they didn't have polynomial time algorithms, or were actually broken. So once again, we were kind of in this unfortunate situation where we had conjectures that were false. And then finally, there was another approach that several of us explored, where we added one more well-studied assumption based on elliptic curves to the mix, something that had been used for 20 years in lots of crypto applications, and certain kinds of pseudorandom generators that are computable by quadratic polynomials. Okay, we needed to conjecture that these kinds of pseudorandom objects existed. And again, this seemed very nice, very clean. But once again, this conjecture was refuted, and in fact, in a quite beautiful way, quite a revealing way. Something really helped us actually later on. And this is also work by one of your colleagues at Harvard, Barak, and several others, in which actually it was methods from continuous optimization. So methods based on semi-definite programming and the sum of squares hierarchy that were applied to, again, refute the pseudorandomness of these quadratic objects. So these objects that are computable by quadratic functions. So, once again, another conjecture that's once again refuted. So, as you might imagine, this was something of a traumatic period. And I can definitely say that I had students that I was working with on this problem. I was trying to convince them how beautiful and important I/O is, and this was just a bit too much for them. It was just the sort of a run for the exit started happening once sort of this kept on going on. And now let me kind of just take a step back and just sort of reflect on this for a moment. So, what do you do when all your sort of areas or fields, simplest conjectures get refuted? It seems like kind of disturbing situation. And indeed, it is disturbing, and it's not very fun when you're in the middle of it, as I was, and as my colleagues and co-authors were. And for those of you who don't work in cryptography, you might be reasonable for you to think, but surely in cryptography, this sort of thing must be common. After your whole field is based on conjectures, right? But it turns out this is not true. It's not really true. This sort of thing is not very common. For there to be many, many conjectures that all turn out to be refuted and one after the other. And the reason why it's not are really just the standard reasons that happen in all of mathematics. Of course, we all know that conjectures are very important, but most false conjectures get refuted by the authors before the writing process, right? Before the publication happens. After all, conjectures look very enticing to authors of the conjectures as well. So that's certainly one very important reason, and I will definitely tell you that as one of the major purveyors of these kinds of conjectures that got broken, we had many dozens more that we broke ourselves and that never made it to the public eye. It was only the ones that we stood over, thought about for weeks and weeks, that we thought, okay, what, let's ask for the community's input on these conjectures, and we put them out. So that's, of course, one sort of standard reason. And then this other reason, if you'll allow me to have a little bit of moral philosophizing, is that, these are scary. It's scary to make conjectures. And sometimes if you make too many conjectures that turn out to be false, then, it can lead to people questioning your motives. No one ever actually said this to me, but someone did, kind of intimate that, I have quite a racket going on where on odd years I publish conjectures, and on even years I refute those conjectures that I made the previous odd year. So this is not fun, right? And I think that's kind of sad, actually, because I think that indeed conjectures do drive mathematics, do drive all these fields, and it's very important when the problems are big enough, when the goals are sufficiently important for us to do it. And for those of you who are a little younger in the audience, especially, sorry, was there a question? No, all right. But for those of you who are a little younger in the audience, I really want to bring your attention to a really wonderful article in Nature published by Steven Weinberg, who is famous for his work on unifying electromagnetism with the weak nuclear force, in which he wrote the following sort of personal reflection. He said, a student told me that he wanted to go into general relativity rather than the area that I was working on, elementary particle physics, because the principles of the former were well known, while the latter seemed like a mess to him. It struck me that he had just given a perfectly good reason for doing the opposite. My advice is to go for the messes. That's where the action is. And I love this quote. And there's no question that obfuscation has been sort of a wonderful mess for many, many years, including all of this work with different kinds of conjectures that turned out to be false. And now, I don't want to be too cavalier. Obviously, we shouldn't just be stubborn people who just keep pushing against something for no good reason whatsoever. So, why is it? Why should one continue when your conjectures keep turning out to be false? And first of all, there's no question that this is a different kind of theory work than is typical in the math community. I mean, there is some sort of untamed wilderness that we're approaching in a different way because we're trying to find the appropriate conjecture, right, for achieving a particular goal. So that's a little different. But one of the things that I would want to point out is that obviously I'm here speaking to you because it did work out, as I'm about to tell you. But we always actually had confidence. So my co-authors and I, we were never really dissuaded by all of this. And the reason was really kind of two main reasons. One is that all of these refutations were actually really insightful. They gave us really, really clear, don't go here signs that came up for certain areas. Now, of course, if all we saw was don't go here signs, then we should give up, right? But that wasn't the case at all. So throughout this whole process of producing conjectures, in fact, we always felt like we had an incredible amount of freedom. There were enormous degrees of freedom for us to look at in trying to make our way, connect different conjectures to I/O. And I think the fact that we always felt that that degree of freedom was still there to us, even after all of these refutations occurred, is sort of a good working principle that I would suggest. If you keep getting shot down, then you should ask, do you still have degrees of freedom that you perceive despite these new lessons, obstacles that you've learned? And that was definitely the case for us. And indeed, that brings us to today. So in a joint work with my with my outstanding PhD student, Ayush Jain, who's on the job market right now, and my really excellent, super awesome collaborator, Rachel Lynn, who's a professor over at Washington, we, late last year, were finally able to achieve I/O based only on well-studied assumptions. And these three, I've briefly at least acknowledged before. The new one that we added to the mix is something called LPN over ZPN. I'm going to talk a little bit more about sort of the crucial role that played in achieving our goal. Okay, so with that, sort of the history part of the talk is over, and I want to start to tell you about our approach, again, at a very, very high level, and focusing more on, especially on how we use ideas from error correcting codes, from the theory of error correcting codes, to achieve our result. It's also, of course, an excellent place to answer questions, if there were any, about things we've discussed so far. Also happy to talk about those philosophizing things at the end of the talk. All right, if there are no questions, let me jump straight into it. So what is our approach? How are we going to do this? So the first thing we're going to do is we're going to change our perspective. So instead of thinking about I/O directly, let's think about encryption. Now, typically, when we think about encryption, we want an encryption scheme to hide the message that you are encrypting completely, right? We don't want to know anything about that underlying message. Instead, suppose we had some sort of weird leaky encryption scheme, okay, where the encryption of X actually lets you learn certain very specific functions of X. Okay, so it leaks certain information, but very specific information. Okay, and what I mean by that is we actually have a collection of functions, a collection of these k+1 functions, f0 up to fk. And what the encryption of X reveals is f0 of X, f1 of X, up to fk of X. Okay, and on the other hand, the encryption guarantees that if I have two different values, x0 and x1, if all of these functions agree on those two different values, then the encryption should look indistinguishable from each other. In other words, if I look at the encryption of x0, first I figure out everything that it leaks, right? And I confirm that that's the same as it would have been leaked on encryption of x1. And if that's the case, then I can't be sure whether I actually saw an encryption of x0 or encryption of x1. Okay. So this sort of change in perspective leads to the notion that we call functional encryption. This is something that we introduced back in a joint work with Brent Waters back in 2005, and then sort of first fully formalized it in a work with Bonnet and Waters in 2011. Okay, and why is this relevant to I/O? It's relevant just because of a very simple sort of duality between programs and data, right? What I can do is I can just let X be the program P that I want to obfuscate, right? And now my functions can be the following: like F0 of P can simply be P evaluated 0. F1 of P can be P evaluated 1, and so on and so forth, right? So this is obviously a function of the description of the program that takes a description, just evaluates it on various points, right? And once we do that, then we see that such a functional encryption scheme, the way that I've written it here, would just satisfy the definition of I/O. Now, I want to let you know I'm lying to you in a few subtle ways about exactly what functional encryption means, and it's a slightly different definition that I'm using here than the one in the papers, but this is still the overall idea. Okay? I'm not lying to you about the overall idea. Okay, so what that means is that if we want to achieve I/O, we should instead try to construct this type of functional encryption scheme that works for these kinds of functions, right? So just to recall, right, we want to encrypt a program P that lets you learn the evaluations of the program, okay? And the encryptions are indistinguishable as long as you have functionally equivalent programs, right? And the first observation is that, of course, it would be trivial to achieve this just by letting the encryption itself be the evaluation of the program at all of the possible input points, right? This would obviously let you leak, it would leak exactly the information that you want to know. And on the other hand, if P0 and P1 are functionally equivalent, this vector will be identical. So it will certainly satisfy the definition. But of course, this is not going to work for us. And the reason, if we go back to thinking about I/O, is this is just too big, right? If we do this for I/O, right, I wanted a polynomial time transformation. So I wanted that the size of my encryption, now if we reinterpret it in the sort of language of functional encryption, the size of the encryption should be polynomial in n, right? Where k is something like 2 to the n minus 1, right? Because we're sort of evaluating at all possible points. So clearly this trivial solution will not work, which is good. I mean, otherwise I/O would have a trivial solution. But it turns out that, and sorry, let me just quickly mention that, in other words, what we're asking for is an encryption size that is polylogarithmic in k, right? Log k is n, we want polynomial in n, okay? But it turns out that this previous work that I also mentioned earlier, starting with 2 concurrent and independent works, one by a couple of my students, Prabhanjan Ananth and Abhishek Jain in 2015, and by Bitansky and Vaikunthanathan concurrently and independently, and then several other works, Lin et al. And Bitansky et al. that built upon that, actually showed that we don't need to go all the way to polylogarithmic complexity. It's sufficient if we can just get some polynomial advantage over the trivial scheme. So if I can just achieve an encryption size, which is like k to the 0.99, that's enough. We can actually bootstrap from that, sort of slowly increasing the input domain of our program recursively, and start with something like this and end up with something like this. So that's what these works showed. So that's great, right? It makes our job a lot easier. We want to now just have an encryption scheme that is a little more efficient than just writing down the entire truth table of the function that we want to that is implemented by the program that we want to encrypt. Okay, so this is our new goal, right? Great. And so the next question is, if we want to build such an encryption scheme, well, what kind of functions Fi of P do we know how to do this for? We've looked at functional encryption. Functional encryption has been around for well over a decade. So you know, what have we figured out how to do so far? I'm just rewriting our objectives here. Well, it turns out that building on really a vast literature that has come up in the last couple of decades, that all began with Miller's beautiful algorithm for efficiently computing the Weyl pairing over elliptic curve groups, something that has had just incredible applications in cryptography. In some recent works that were by the three of us, also together with Prabhanjan Anant, Matt, and Romain Gay, we were actually able to show how to do this for any function fi that have the following two properties. So they can only be quadratic. They can only be degree 2 in the actual description in the description P here. In the input, I should say, in like the secret input to the encryption, the thing that we want to encrypt. But they're also allowed to be constant degree, any constant degree, in some additional public information. Okay, and I'm sorry I won't define that extremely precisely for you, but that is going to play an important role, and hopefully you'll see what I'm talking about soon. Okay, so this is what we were able to do thanks to elliptic curves and efficient computation of the Weyl pairing. And indeed, the fact that the Weyl is a pairing is the reason why this is degree 2. So this is not some coincidence. You know, there's a reason why we're stuck at quadratic here. Okay, and kind of the new ideas really were in actually getting this degree, this constant degree in additional public information to work out. That was really the contribution of this sequence of works. So great, that's what we know how to do. But remember, what do we want, right? We want these functions that are where like f0 of p is p of 0. That can be really complicated, right? After all, if the program is some arbitrary polynomial size Boolean circuit, then fi has to somehow read the description of the circuit and then evaluate it and see what the output is. So in general, it can be really complicated. Thankfully, again, we have a lot of previous work, really classic work actually, due to Yao and Applebaum, Ishai, and Kushilevitz, which show, assuming certain kinds of low degree, certain types of constant degree, low depth, constant depth pseudorandom generators, it turns out that without loss of generality, we can assume that these functions that we need to construct I/O to get us all the way where we want to go, in fact, are constant degree. They can be constant degree. That constant is bigger than 2 though, but it's some constant degree. And in fact, not only is it constant degree, but in fact, each output only depends on D, a constant number of bits of the input description of P as well. So we can actually get quite a bit of reduction in complexity of these functions f in terms of what we need to be able to achieve to obtain I/O. But we don't know how to get all the way from degree 2, or at least we did not know how to do that prior to our work. Okay, and really this is the core challenge. So reconciling the difference between what we know how to achieve, which is quadratic in the description, and what we need to achieve, which is some constant degree greater than 2 in the description of P. Right? So how can we bridge these things? Okay, and that's really where our new work comes in. So in our work, the work with Ayush and Rachel, we have sort of 2 key ideas that we introduce. The first one is that instead of trying to directly implement fi of p using a quadratic polynomial, let's instead just try to approximate fi of p with a quadratic polynomial. And what I mean by approximate here is a different kind of approximate. Like I mean it in the sense that fi of p will equal gi of x for almost all the i's. Right? So for almost all of the points where we want to evaluate the function, we're going to be able to do it with a quadratic polynomial. Okay, but in some places we're going to give up. Okay, And as you'll see, this will actually be randomized. So there'll be an additional random component to the input here. So in fact, the eyes on which it works and the eyes on which it doesn't work will be different based on the random input, okay? And then finally, once we have done this approximation, we're going to see very, very briefly how we can use another quadratic polynomial to error correct so that the final polynomial will in fact be a quadratic polynomial that computes fi of p by summing the approximately correct polynomial together with another quadratic error correction polynomial, okay? And as might be apparent just by the language I'm using, both of these ideas crucially use ideas from coding theory, from the theory of error corrected codes, in particular from the theory of random linear codes, okay? So let me use that to tell you about one of these long-standing conjectures that we'll be using and how we'll be using it, okay? So this long-standing conjecture is called the LPN conjecture over ZP. It was first put forth in a cryptographic context by Blum et al. In 1993, and then we kind of wrote it in a more general form in a work with Yuval Shai and my former student Manoj Prabhakaran back in 2009. But in fact, the conjecture dates much further back. So it dates all the way back to the 1950s. So all the way back in the 1950s, Richard Hamming and others looked at what we call linear codes, and in particular random linear codes. So what's a random linear code? A random linear code is defined by a matrix A that we will think of as being a tall and skinny matrix. It'll have n rows and L columns, okay? L is something that we think of as being polynomially smaller than n, okay? So think of L as being maybe the 100th root of n, something like that. Okay, so much, much smaller. So the dimension of S is much, much smaller than the number of rows in our matrix A, okay? And we encode this short vector S by just multiplying it by A, right? So we get A times S, which is our code word C, okay? And in fact, again, all the way back in the 1950s, in really classic works of Gilbert and Varshamov, they showed that such random linear codes actually have extremely strong combinatorial error correcting capabilities. So if you choose such a code at random, and then what you do is you add a sparse error to the code word, then you can uniquely recover the original message S with overwhelming probability combinatorially, meaning that with overwhelming probability, there will exist a unique S that explains what we see, right? So
you have 15 minutes left.
Okay, very good, thank you. So again, this has been very, very heavily studied since the 1950s. However, in all those decades, in fact, no efficient decoding algorithm was ever discovered. And again, this is despite really decades of intense study in the error correcting codes community. And in fact, even algorithms that are sub-exponential in the dimension L, the dimension of the secret S, have not been known. And so this gives rise to a very natural conjecture, right? The conjecture is that in fact, this is hard to decode. That if I pick A at random, I pick S at random, pick E to be a sparse random vector, where by sparse random, I mean that only with probability 1 over L to the delta for some constant delta greater than 0, we let EI be a completely random element of ZP. And otherwise, it's just 0, okay? And by the way, we cryptographers, when we write ZP, we mean Z mod PZ, okay? So, so that's our notion, right? And a very natural conjecture is that given such randomly chosen A comma AS plus E, it is hard to recover S, okay? And in fact, it's sub-exponentially hard to recover S. That's the conjecture. And indeed, that's the conjecture that we make. And it turns out that thanks to a well-known search to decision reduction due to Michancio and Peikert back in 2013, the fact that we cannot recover S given AS plus E actually implies that AS plus E is pseudo-random. So in fact, A comma AS plus E looks like A comma completely uniform to any sub-exponential size adversary. And when I say looks like, I mean exactly that definition I talked about earlier, where the probability that the adversary outputs 1 is, in this case, sub-exponentially close in the two cases. Okay. And in fact, as I mentioned, this has been studied for a very long time. This is a slide that I stole from a friend of mine, Geoffroy, that just shows a few of the attacks that have been considered on this problem. And it turns out that despite all of these decades of attack, the best known attack is basically trivial. It basically runs in time 2 to the order of L to the 1 minus delta. And if you think about it, that's roughly the amount of time that it would take if you just guessed at random places where you think there are no errors and just use Gaussian elimination to try to recover S, right? So if you just did that, that would already take you roughly 2 to the L to the 1 minus delta time. And the best known algorithm is the same order of magnitude. So really, despite all these decades of work, there's been almost no advancement really in terms of the running time of decoding here. And we're actually making a relatively conservative assumption, right? Because the best known attack, the best known algorithm is 2 to the L to the 1 minus delta. And we're only assuming 2 to the L to the epsilon security for any constant epsilon greater than 0. Okay. And again, for any delta greater than 0. So both epsilon and delta could be 0.001. And that would be enough for us in terms of the conjecture. Okay. And it's also a wonderful win-win type of conjecture, because if this conjecture turns out to be false, maybe it's true, it's possible, but it would actually be a breakthrough in the theory of random linear codes. So that's also a nice thing that we have here. Great. So I only have a few minutes left. So maybe just very, very quickly, let me sort of give you the rough idea about why these random linear codes are useful. So remember, I'm trying to somehow approximate my function f with a quadratic function. In fact, even just a linear function. Okay. So here's the observation. Because of the LPN assumption, if I use AS plus E, if I take AS plus E and I add the description of P, if I add the input P to it, right, then I'll get some value B. And because AS plus C was already uniform, adding P to it still makes it look uniform, right? So in this way, we see that A comma B is actually an encryption of P. And because it's an encryption, it can be made public, right? We say that an adversary that gets to see A and B can't recover any information about P. Okay, again, that falls from the pseudo-randomness of AS plus C. Okay, why is that useful? Well, it lets us do just a simple change of variables, right? Observe that B minus AS is P plus E, right? So in other words, B minus AS is almost P, right? It agrees with P in almost all the places except for a few random spots where it doesn't agree because of our error vector E, right? Well, what that means is that Fi of B minus AS is equal to Fi of P plus C, right? Which is almost Fi of P, right? Almost everywhere. And finally, we recall that the dimension of S is actually really tiny, right? L is like N is like the 100th root of N. It's like a very, very tiny polynomial in N, okay? And why is that useful? It's because what we can do is I can just pre-compute all the constant degree D monomials of S, right? In a tensor. I can just create a tensor of S with itself, right? And in this way, I have now computed all the degree D monomials of S. And now, in fact, I can compute Fi of B minus AS just, in fact, with a linear function, right? It doesn't even have to be quadratic. Here, quadratic just helps us shave a few factors here and there, but this is just a linear function in our actual secret S, right? Using this public information A and B, which we're allowed to have polynomial dependence, constant degree polynomial dependence on, but everything else is, the only part that's secret here is this tensor of S, which is still small because of the way that we've chosen the parameters for our random linear code. Okay, and just this simple idea lets us get an approximation of our function with a quadratic. In fact, even with a linear polynomial. And I realize I did go over that very quickly, so please ask if you have some questions about it. And then, just because I did want to leave time for questions, let me just very quickly talk about the second idea, which is this error correction. And really, the key idea here is that after we've done the first step, right, the only places where fi of p plus c is not equal to fi of p is just a few places that were affected by where ei was non-zero, right? So it's actually extremely sparse. The set of spaces that we are not correct on is extremely sparse. And then all we do is we just arrange that sparse vector in a matrix, and then just factorize it out into into the outer product of two vectors, right? And here I'm just giving you the example where there's only one place where there was an error. In that case, it would be the outer product of these two vectors that are of length square root of the original vector. In general, it won't be quite that simple, but it's really the core of the idea is just that simple. It's just a sparse matrix factorization. And here we do crucially rely on the fact that we're allowed to do quadratic computations in order to achieve that. And that's the crux of it. Obviously, I've hidden many, many details under the rug here and not explained many of the steps in the ladder that we use to get the result. But that is how we are able to achieve I/O. Again, just in the interest of time, I'll just mention these other problems that we're also conjecturing. The LWE problem is very much like the problem I already showed you. It's just that instead of sparse error, we have small Gaussian error. It's been very well studied for the last decade and a half, and is known to be related to classic questions related to the shortest vector problem. We also assume the existence of pseudorandom generators that are computable by constant depth circuits with polynomial stretch. Again, something that's been extensively studied, falls from one-wayness conjectures, and is perhaps the least structured of all of the assumptions, all of the conjectures that we're making. And then finally, we have this SXVH assumption over elliptic curve groups that has been really extensively used in cryptography over the last couple of decades. And that's it. All the assumptions are made against sub-exponential time adversaries that I mentioned. So just to conclude, what have we seen, right? What we've seen is this kind of remarkable turnaround with regard to this notion of I/O. It has incredibly remarkable implications to the theory of cryptography, to conjecture-based mathematical cryptography. And now finally we have its security that is based on long-standing hardness conjectures in cryptography and complexity theory. I should mention that we have many, many steps in this. And as a result, the method is polynomial time. You know, we can prove that it's only a polynomial overhead, but that polynomial and the hidden constants in the polynomial are insane. So they're so big that we haven't even bothered to work them out, but they're very far from being implementable on Earth. You know, maybe in some other universe there'll be enough room to implement it, but probably not on Earth. So what's next? Of course, we think there's a lot to be gained, even in terms of efficiency, but also just in terms of simplification. We're quite optimistic about this. We already have some things in the works on more direct constructions. And really, I also think this is just a great reason to think about yet more conjectures, yet other directions that we can explore, which may lead us back to some false conjectures along the way, but let's try to explore the space more fully, understand really what are the space of hardness conjectures that we can use to build I/O, In particular, can we get post-quantum security? I'm optimistic, but don't know how to do that. And actually implementable I/O would be great. So with that, I will conclude and end here. Thank you. I think I just barely made it on time.
Yeah, quick talk.
Thank you very much, Professor Sahai. We
Thank
learned
you.
a lot. We still have some time for questions from the audience. While people are thinking, could you please comment on vulnerability to quantum computers?
Yes, great question. So let me just mention. So in fact, the assumption that I actually did have time to tell you about, which was this the LPN assumption, this one. This one, actually, we are not aware of any quantum attacks, and in fact, it's far from that. It's given the state of our understanding of quantum complexity, which is of course in its infancy, it's actually a quite plausible conjecture to make that this assumption is post-quantum secure, that even quantum sub-exponential time algorithms cannot decode these kinds of error correcting codes. Similarly, the Gaussian version of that assumption is also believed to be post-quantum secure. Similarly, the existence of PRG is considered computable by constant depth circuits. In fact, this is really the most unstructured assumption that we have. We have absolutely no idea why or how a quantum computation would help with this. It's this final assumption where we assume something over elliptic curve groups. This is vulnerable to Shor's algorithm. So Shor's algorithm defeats basically lets you compute discrete logarithms in sort of any periodic group structure, including the kind of elliptic curve groups that we're looking at. And so it is true that because of Shor's algorithm, which of course we don't have any idea how to implement practically right now, but assuming one day quantum computers will eventually implement Shor's algorithm, then yes, they will allow you to break this assumption, which will invalidate our conclusion for post-quantum security. So really, the main question is, can we avoid this? And as I mentioned, the place where we're using this is for building the sort of underlying functional encryption scheme that can support quadratic function evaluation. And there we really are using something quite remarkable about these elliptic curve groups, the fact that they have these efficiently computable whale pairings. So to get an alternative to get around that is a really interesting question. I think, I don't know how to do it right now. You don't have to follow this strategy. There are other strategies for constructing I/O that have come out recently that are really potentially promising, but not yet based on long-standing hardness conjectures, still quite new, evolving, and subject to attack kinds of conjectures. But yeah, that's where it lies. Thanks for the question.
Thank you. Are there any more questions from the audience? Yeah. Okay, here is a question. I will read it to you.
Yeah,
I know that I/O has a lot of important implications in cryptography, and the question is about related areas such as privacy and algorithms that work against an adaptive adversary. Could you please say a few words about the implications that I/O has in this context and what the new results may mean? This is a question from Omri Ben Eliezer.
Okay, excellent question. So, very good. Let me give you a couple of ways of answering that question. So one thing that I didn't mention to you, which is really fascinating about I/O, is that I/O obfuscation is a kind of best possible obfuscation. Okay, this is something that was observed in a work of Goldreich et al. Several years ago. And what that means is that, let's assume for a moment that you have some function and you just believe that there exists a black box obfuscation for that function, or for that family of functions, or for that distribution of functions, in fact, right? Then, in fact, the I/O obfuscation of that family of functions will be a VBB obfuscation as well, assuming sufficient padding. Okay, so so that's actually a very powerful way of thinking about what the implications can be. An example might be a little related to what you were talking about, is in the area of let's say adversarially robust machine learning, right? So if you know about the area, for those of you in the audience, more generally, we have these very powerful, apparently powerful, neural network algorithms that are trained via stochastic gradient descent, right? That seem to learn really well, to seem to have excellent generalization and all of that. However, they're extremely vulnerable to adversarial examples. So if I know the neural network, then it's usually not that hard to do sort of gradient ascent, right? Where basically we'll start off at some position that's nicely classified and then sort of try to, as quickly as possible, move to some other classification. And with only modifying a very small amount of the image or the whatever it is that we're classifying, you can end up with an incorrect classification. However, using I/O, right, using obfuscation in general, if we were able to obfuscate the neural network that was learned, right, then it at least makes the challenge to the adversary much, much harder, right? Because then the adversary will only have black box access, assuming again that we can virtual black box obfuscate that function. You will only have black box access to the underlying classification function, which again, there's a lot of research that's still going on here. It's not a settled problem by any means, but there's at least evidence that obtaining adversarially robust learning algorithms and classifiers against black box access to the algorithm is an easier problem than doing it when you have full access to the underlying model. So that's sort of one example of how I/O could potentially have applications, even to really like a very diverse, very different sort of area from cryptography. Hopefully that was helpful.
We have one more question from the audience. Anna Bistrik is asking, how energy efficient the perspective I/O implementation will be?
I'm sorry, I actually couldn't hear you. There's just a problem with the internet. Can you just repeat the question one more time?
Sure. How energy efficient the perspective I/O implementation is going to be, in your opinion?
Very good. Okay, so again, as I mentioned here in the conclusion slide, I mean, I do not suggest anyone to implement our current scheme. In fact, even just estimating the constants is crazy. So right now, I'm guessing, I haven't actually worked it out, but I'm guessing if one actually tried to take our scheme as published and implement it, it would take more energy than Bitcoin. It would be insane and not at all recommended or reasonable. So that's definitely an area where there's a lot of work to be done. And I think the earliest steps are simplification. So again, we've had this long, complex history where we've combined many different fairly deep aspects of mathematical cryptography, conjecture-based cryptography, to achieve our goal. And now that we actually see how it works, there should be ways of simplifying it considerably, and getting to something where we can talk about energy efficiency would be a really wonderful thing. Right now, we're not there yet. Frankly, I'm not in a position to be able to answer that question right now. Hopefully one day soon, we'll be able to implement IO obfuscation using less energy than Bitcoin? Let's say that's definitely an open question as of right now.
Let me see.
Okay, there is still a question from Anna Bistrik again. You have mentioned SXDH assumptions over elliptic curve groups in Shor's algorithm. Is Shor's algorithm vulnerable potentially? How long would it take to catch up? A week, a year?
Okay, if I understand the question, you're asking about how realistic is that? I may be misunderstanding, but I believe your question is about how realistic is the Shor algorithm attack on the SXDH assumption over elliptic curve groups. Is that also your understanding, Sergey?
That's my understanding as well.
Good, very good. So I'm certainly no expert in constructing quantum computers, but my understanding is that we are extremely far from being able to construct a quantum computer that can do Shor's algorithm. In particular, these elliptic curve groups, the number of qubits that we would need to maintain coherence for in order to be able to run the attack would likely be at least in the thousands and maybe in the large thousands, depending on the underlying quantum computing architecture. So my understanding is that we're extremely far from being able to actually attack the SXDH assumption using any existing quantum computing technologies. Now, of course, that can change very rapidly, and I hope it does. That would be a wonderful advancement. I think that if we get quantum computers, then I'm personally the most fascinated by the question of, will it tell us something new about quantum mechanics, right? Will it actually tell us new physics? Will new physics emerge from the construction of effective large-scale quantum computers? But if one day we do have very fast quantum computers that, let's say, are as fast as my laptop and can have as many qubits as my laptop has RAM, I mean, we're extremely far from that. But if we were, then SXDH would fall quickly. It would just be a few minutes to run using Shor's algorithm. Or I don't know, a few seconds, I don't know, but very, very fast.
Peter Shor will be one of the next speakers on this series, so we will see what he says.
Sounds good.
We have a question from Pierre Galissant. Thank you for the presentation. You show the why box contest as an example of obfuscation. How close white box cryptography and IO are according to you?
Very good. So I would say that, excuse me, white box crypto, like in particular the white box contest, if you look at it at first glance, it looks much more related to VBB obfuscation, virtual black box obfuscation, and there just a very direct comparison. Okay. However, it turns out that in these white box contests, at least, the kind of breaks that we see are total breaks, just complete breaks. Entire key recovery attacks are typically found in practice. So that would also be a break on IO, right? The point is, like, if one was able to take an IO scheme, implement it, and submit it, like, of course we can't right now because it would just take too long, but if we actually had an implementable version, resubmitted it, then there are ways. Let me put it this way. First of all, I would conjecture that it would easily win. They would not get broken because of the plausibility of a virtual black box obfuscation existing. And remember, again, IO is a best possible obfuscator. So if it is possible to virtual black box obfuscate a particular distribution of functions, then it is also possible to achieve the same level of security using IO. So I gave a bunch of answers. I hope some convex combination of them is a is an answer to the question that was actually asked.
I don't see any more questions.
All right.
And given that we are pretty much out with our allocated time, let us thank again Professor Sahai for the great talk. Thank you.
Yeah, it's a great talk. Thank you very much indeed.
Thank you. Thank you. It was a pleasure.
Hope to see you sometime in Cambridge.
That would be great.
Yeah.
All
Thank you indeed.
Yeah.
Okay.
Yeah.
Thank you.
Bye.